Gino. No one comes in your book. You're here. That's all that matters, right? Gemma. Bree, Terry. Should have just went around that. They're not in other order. Reckenbaugh, I can't read the first. Jesse Rose. Wally Sheridan. Colin Snyder. Sadie Spencer. Kelsey Thompson. John Winston. Did you get yours back?
Yeah.
Oh, okay. Kelsey Thompson, John Winston. Is there anyone that didn't get it back? Anyone else that didn't get it back? This week we covered 2 chapters. Sounds like a lot, but it's not. Chapter 12, I only take what you need for chapter 13 because it's all probability and no one likes it except for me. So I take what the little bit of it that you need for chapter 13 because I think chapter 13 is an important chapter. So I always cover it. The exam did really well. When you combine the 2 together, they're 100 points. So 100 to a 90 would be an A. 89 to 80 is a B. Oh, and the 5 extra credit points was added on. It was added onto the take home, except for one person because they hadn't turned the take home in. So I put it onto the in class one so I wouldn't forget. So that's the grading scale if you add the 2 tests together. There were 18 A's, 9 B's, and 3 C's. Oh, one of the take homes was blank. So if you're seeing a 0, well, everyone got, well, I don't know if I had them together today. Just double check. Just the blank ones. So we're covering 2 chapters, which means you have 2 homework assignments. Was gonna throw them together, but I didn't. I left them separate. I think we will get through both chapters, the outlines today, and then we'll go over the homework on them next class. And then if we do, we'll have the group assignment on Friday. If we don't, then we'll just finish the homework on Friday. Next week is our last week. We will just review the whole week. Your final was written on the attendance. It's at 8 a.m., so be careful of the time. It is Friday of finals week, December 16th. at 8:10 a.m. in this. If you want to take it earlier, let me know. I do have a final Wednesday at 10:30. So if you wanted to take it then, you could. Just let me know and I'll let you know what room it's in. I don't know what day my daughter has to be here for her finals. But if you do want to take it earlier, that's fine with me. See when your other finals are and we can figure something out. If you have more than 2 finals on the same day, you can get one moved. So if it is on Friday, let me know. Okay. Chapter 12. Chapter 12 extends on probability. And when you're doing more than one thing, tossing a coin and rolling a die, picking 2 cards from a deck of cards, it's important to know if it's an independent or a dependent event. First one, independent one does not rely on the next one. They are independent of each other. It does not change the probability. So independent does not depend on what happened before. If we roll a die and then we roll the die again, when I roll this one, whatever number I got isn't going to reflect the probabilities on the second one. It's still the same 6 numbers on the die, as long as it's a fair die. One isn't going to affect the other. With independent events, can find each probability and multiply them together. So if we wanted the probability of rolling 2 6s with an independent event, the probability of rolling the first one is 1 out of 6. The probability of the second one is 1 out of 6. It doesn't matter what happened the first time. It's not going to change my probability the second time, so it's independent. If we're pulling 2 cards from a deck, can it be independent? When I pull that first card out, if it's an ace, there's how many aces in a deck? 4. So the chances of pulling an ace is 4 out of 52. When I go to pull the second card, have I changed the probability? Depends. How could I make sure I don't change the probability? Put the card back in, and then it does it, and it makes it independent. But if we don't replace it, then it changes it. So pull 2 cards from a deck. So we place the first card before pulling the second one, that makes it independent. Because then there's still 4 aces and 52 cards. If we pull 2 cards without replacing, that makes it dependent because the second one depends on what happened the first time. So we have 4 aces, 52 cards. When we pull the first one, 4 out of 52. But now we're not putting that ace back, so there's only 3 aces out of 51 cards. You've changed the probability. That makes it dependent. Because the second one depends on what happened in the first. Any questions on the difference between the two? So if it's changing the probability, it's dependent. Depends on what happened before. I think I had a little explanation there too. With independent events, can find each probability and multiply them together. Also, to find total number of outcomes, multiply the number of outcomes together. Now, this only works for independent. When you're finding the number of outcomes, well, I guess you could make it work on dependent, you just have to be careful. So doing it with independent, when we pull the first card, there's 52 outcomes because there's 52 cards in that deck. We put it back in. So when we pull the second card, there's 52 cards. So to find the total number of outcomes, you just find out each one individually, how many outcomes, and just multiply them together. So there's 2,704 different ways to pull 2 cards out of a deck of cards when you're replacing. When you're not replacing, you need to be careful if you're finding number of outcomes. When we pull from the deck, there's 52 cards. But because we're not putting it back in, the next one has 51. So there's 2,652 outcomes. So you can use it for independent, just need to be careful because your probabilities have changed. And these are always just your total outcome for each individual. So if we had we're rolling to die, how many outcomes are there? First of all, if we roll 2 die, are they independent or dependent? It's the first one I used. How many outcomes are there when you roll the first die? 6. And 6 for the second die, because they're independent, they don't change. And 6 times 6 is 36. So there's 36 different outcomes. Any questions on that? How about so if we're going to this example, toss a coin and roll a die. We know they're independent of each other because no matter what I get on the die, it's not going to change the head and the tail on the coin. Look, how many outcomes are there? So if we're tossing a coin and rolling a die, how many outcomes? 12. Go ahead and list them all. When you toss a coin, there's 2 heads or tails. Rolling a die, since we're assuming normal die, 1 through 6. Now, one thing you can do if you can't think, I mean, this one's not too hard. You could use what's called a tree diagram. That would be the possibilities for rolling a die. And then on those, we toss our coin and we would have a head or a tail. And then if you were doing another thing, you could put it onto that. So you could use a tree diagram to make sure when you're not finding one. Any questions on? Find the probability of a head and a 4. Are those 2 probabilities the same? You need to be careful because they're not. The first one means it has to have a heads and a 4. This one means it has to have heads or 4. So that means it could be both, but it doesn't have to be. We know that there's 12 outcomes, so that's our denominator. A head and a 4, there's only 1. So it's 1 out of the 12. And if these are reducible, you don't need to reduce. When you're doing probabilities, sometimes you want to add them together to check things, so you don't want to reduce. Keep the denominator the same. So everyone agree with this one's 1/12? Because there's only one of these that's a head and a 4. But heads or 4, this whole top row is heads. Now the 4 here is already included, but there's also this one. So it's all of these plus this one, 7/12. It's easier to find the probabilities when you write them. But some of them are too large and you don't want to write them. So you have to think about what they are or find them individually. Any questions on that? Toss two coins. So if we toss two coins, how many outcomes are there? Two times two, four. Go ahead and list them. Finding them all. A lot of times, students are stuck with 3 of them instead of 4. But the order matters. You can have a heads and a heads, a head and a tail, or a head or 2. This is a case where doing the diagram would help. So a heads and a heads, a head and a tail and a head, and a tail and a tail. Any questions on that part? Probability that they're both heads is 1 out of the 4. So it's good to find the number of outcomes because that's always your denominator. Now, since we wrote the whole list, since it's only 4, the probability they're not all tails is just omitting this one, so it's 3 out of 4. You could also go 1 minus the probability both tails. So when you have a larger amount and you can't count all of them, subtract the 1 that's not included. Now, in this case, we could have just went 1, 2, 3, because this is the only case that is all both tails. We could go 1 minus 1, 4 to get our 3. It's just another way of finding it. Probability has a lot of different ways of finding them. Remember, you can write them as a fraction, decimal, or percent. If it's like 1/3 where it keeps repeating, I don't want the decimal. But if you don't have to round it, like this 1.75 would be fine. So if we toss a coin 10 times, how many outcomes are there? You take 2 times 2 times 2 times 2, because each time we're tossing the coin and it's not affecting the next one. So it would be 2 to the 10. And I think we talked a little bit about this the one time with the football team that won so many. 14 in a row, I think, Chicago Bears. So there's 1,024 different outfits. Of course, we don't want to list all those. But if we wanted to find the probability they were all tails, well, if they're all going to be tails, that would only be one way for that to happen. Just like here, there was only one way that they were all the same. So the probability of all tails is only one way that can happen out of the 1,024. I don't think we want to add all of them up to find the probability. They're not all tails. But we know that that would be the same as 1 minus the probability all tails, because the only one that wouldn't be included in here is all tails. So the probability of all tails, 1 out of 1,024, subtracting them 1,023 over 1,000. Any questions on them? Chapter 13 is contingency table. This is one from the book, but it took undergraduate and graduate students in total school. Going across is the number of females and males. So this number 2388 is females that are in graduate school. 4328 here is males in undergraduate. If you want the total undergraduates, total 10,008. The total in the school, 13,433. So if a student is chosen at random, find each probability. The student is an undergraduate. What you do is you find the number in your category and you divide by your total. So the probability the student is an undergraduate, there's 10,008 undergraduates out of the 13,433. Probability the student is a female. Female, they didn't specify undergrad or grad, so it would be the total. 8,068. Any questions so far? Just trying to bring it up so we can get all. student is a female undergrad. So find out how many are female undergraduates and then divide by your total. The only time you're not using the total you need to be careful is when something is given. This one here. So the givens, you got to be careful. But otherwise, you're always dividing by the total, which is 13,000. So female undergraduate, 5680. Well, and then we know it's a female. Because we know it's a female, we can forget about the row of men. Just use this row. So when something is given, use that row or column. In this case, it was given a female, so we're only using that shaded one. Probability they're undergraduate is 5680 out of the 8,068. So when something's given, just narrow it down. There's a formula you can memorize, but it's a lot easier to just use that row or column. So it would be 5680. 8060. So when they give you a given part, only use that row or column. So this time the given part is the undergrad. So I don't know if it'll let me highlight just that column. Oh, it did. Depends on how I loaded it. Because the given part is the undergrad, we're only using that column. We know it's nothing outside of that. So then the probability that it's a female, knowing it's an undergraduate, still 5,680 female, and your total's 10,008. So if something is given, only use that row or column of the given part, and then find the other probability. Any questions so far? A person takes the test to see if he has cancer. There's a couple possible outcomes. See, they use contingency tables for tests all the time. And COVID was another one that they used it. They use it for strep throat. And they tell you a lot of things. Now, you have cancer and the test says so, that would be a true positive because the test tested positive and it was correct. So a true positive is when you test positive and it's correct. So in this case, you have cancer and the test said you did. A true negative is when the test says it's negative and it's correct. So you don't have cancer and the test says you don't. So the true means the test is correct. Negative and positive is the test result. So then if the test tested positive and it was wrong, that means it said you had cancer, but you don't. Where a false negative says you don't have it when you do. I always put my test going across. That way, when we're finding the true positive and false negatives, you always divide by the value below it. So my test will always be set up, the test part going across. And this is saying for the cancer one, testing positive, testing negative, you have or you don't have it. And so those rates are right in these columns, always the same spot. Have cancer, test positive and it's right. Test negative and it's wrong. Don't have cancer, positive is wrong, negative is correct. So as long as your test goes across, these will always be in the same spot. So if you're asked for a true positive rate, it's always here. In your book, they did a test or they found a study for depression. And they want to know how good is the test. This first column is people who are depressed. This one is people who are not depressed. Going across, the test says they are depressed. This one says they're not. If we want to find the true positive rate, true positive was the one you wrote here. So it would be 31 out of 81. No, true positive, they call them rates. You want to write them as a percent. So if we have 31 divided by 81 times 100. So the person is depressed and the test says they are depressed 38% of the time. A false negative. That's this one. That would be 50 out of 80. So that means that someone who is depressed, 62% of the time, the test is going to be wrong. And they're not going to get the help that they need. Any questions on finding these? So when you're finding these rates, the false positive, true positive, all of them, you're dividing by this value below, as long as your test is going across. If the person is depressed, what's the probability he is diagnosed correctly? Well, if they're depressed, that's here. Diagnosed correctly would be this one. That is your true positive. We found the false negative too. A false positive rate. False positive. So you tested positive and it was wrong. It said you were depressed when you're not. That's 34 people out of 291. On a test, you would be asked or in your homework to find these, and then do you think the test is good enough? Well, here, these 34 people, it says they're depressed when they're not. So if they're getting a little more help, it's not going to hurt them. And it's only 11%. But the big thing is this one. People are going there because they are depressed, and 62% of them are sent away because it says you're not. So no, test isn't good enough. I don't think. But it's opinion based. I think that those 38 people, if it's a quick test, those 38 people get help. Then those who it finds are not depressed, maybe they take a little further, more expensive test to make sure. But I still have time. But is there any questions on that? Look over the homework from both chapters. I think we could cover it all. But well, yeah, we should, because we could do it Wednesday and Friday. But make sure you try it ahead of time. It definitely looks different when I do it. Than when we support it. Have a nice day. Yeah. What's your last name? I think we're playing. Yeah. This is like. But you still have it worked out, right?
Yeah. It's on the computer. I've got the video.
If it won't flow, just take a picture.
Email them to you.
He's sitting here. Good night.